Good afternoon and welcome to our Safer Sim webinar series. My name is Jacob Hayden and I'm the program coordinator for Safer Sim at the University of Iowa. Safer Sim, or Safety Research Using Simulation, is a Tier 1 university transportation center with a research priority of promoting safety. And our webinar series features the research projects from within our center. Thank you for joining us today. There will be time at the end of the presentation for questions and discussion. Attendees can use their microphone or the chat box to participate. Feel free to use the chat box at any time throughout the presentation as well, and we will address these questions at the end during that Q&A. This webinar is being recorded and will be shared online after. And with that, today's presentation features a project from the University of Central Florida, and I'm pleased to welcome our presenter, Zheng. I will turn it over to you. Thanks.
Oh, thank you. Hi. Thank you everybody for coming. So today I can present our group's work, use a virtual simulator to evaluate the automated emergency brake system for avoiding pedestrian crash at the intersection under the occlusion conditions. So this PowerPoint has 4 parts. First is background, methodology, result discussion, and conclusions. First is our background part. So the pedestrian crash account for 70% of the total crash fatality. 26 of the pedestrian crash happened at the intersection. Meanwhile, it was also found that obstruction of the driver's view is one of the most common crash reasons for pedestrian crashes. Vehicle speed also are found to have a significant impact on the pedestrian safety for both the crash occurrence and the crash severity. The AV technology such as AEB system provides the tremendous opportunity to prevent this crash by correct the human errors. So many research has been put efforts to evaluate the effectiveness of AEB system based on the simulation or other data source, but most of them is using something like Sumo or Reason, which they cannot consider the occlusion conditions due to the limited of the simulations. So for us, we try to use the 3D simulators like CARLA to simulate this calculation situation. As you can see on the right side, the pedestrian can be detected by LiDAR, but once the pedestrian walks behind the vehicle, it cannot be detected by LiDAR because of the occlusion conditions. So first, I want to introduce the CARLA simulator. The CARLA virtual simulator was used for analysis, was developed by Intel and Toyota, and it gave us ability to change the traffic status and add or remove buildings, change the weathers, or even connect to Sumo to do cool simulations. Also, we can use CARLA to do the sensor simulation, for example, LiDAR, camera, and the radars. The last part is the CARLA simulator allow us to add the pedestrian simulations. Here's one of the example we're using CARLA to add the LiDAR and the camera sensor in the scene. And as you can see, the top part is the LiDAR point cloud visualization, and the bottom is the 3 cameras. Next is an example of the scenario we are using. It's one intersection, and we put 2 vehicles and 1 pedestrian. Here, just an illustration. So the moving vehicle is attached a LiDAR sensor that can detect pedestrians, and the pedestrian will do a causing movement. Here is an overview of how the CARLA simulation works. First, we need to put a vehicle, pedestrian, and sensor registered, and we normally attach the sensor to the vehicles. Then the CARLA will handle the AI part of the vehicle and the pedestrian. For example, they will perform their own localization, collision detection, and the detection of traffic light, and do the motion plannings. For us, we also implement our own Python API for the LiDAR perceptions. That way we can feed the LiDAR percent result back to the vehicles. As that way we can control the vehicle based on the LiDAR feedback. So for our study, the sensor scans the signal of a circle while transmit the detection rate to detect the surrounding object. For this case, it's a pedestrian. The minimum distance between the ego vehicle and the moving object could be used to calculate the time to collision in the TTC. The TTC we apply as a metric to activate the braking signal of the AEB system. Once the TDC is below the specific configure threshold, the AEB system is triggered to react to avoid the potential crash. The braking system response consists of the brake delay and the build-up time until the full brake, which can be expressed in the following equation. As you can see, the equation, the numbers are from the literatures. Here's our first scenario, scenario 1. As you can see, there's left side is the CARLA screenshot, and on the right side is the illustration of this design. So the Eagle vehicle is going through while the pedestrian working on the crosswalk of the Eagle vehicles extending the approach, and the pedestrian is occluded by the yellow vehicle on the left turn line. The second scenario is the Eagle vehicle is going through while the pedestrian is working on the crosswalk of the Eagle vehicles entering approach, and the pedestrian is occluded by the yellow vehicle on the left turn lines. The last one is the Eagle vehicle is going through while the pedestrian is working on the crosswalk of the Eagle vehicles entering approach, and the pedestrian is occluded by a yellow vehicle on the right turn lines. So a total of 216 aging motion status were included in this study, considering the pedestrian initial speed, Eagle vehicle initial speed, offset time of the pedestrian crossing time. Also, we have 16 cases of the AEB control strategy. So there are one case, there's no AEB control. So there's a total 10,368 cases. Simulation were conducted to evaluate the effectiveness of AEB system under the occlusion conditions. So for the evaluation methods, the collision could be determined by the overlapping of the aging contour, which could be calculated by on each time frame. The position of the both Eagle vehicle and the pedestrian at the collision time could be identified by using the feature of the Eagle vehicle and the pedestrian. Relative impact location to the center of the contour edge can be estimated. Impact speed of the Eagle vehicle could be obeyed for the evaluation. So as expected, the higher speed will result more severe pedestrian crash. The duration of the collision could also be obeyed by exploring the effectiveness of the collision on the effectiveness of the AEB systems. Here's our result. So to validate the effectiveness of the AEB under collision conditions, the simulation without the AEB braking system was used as a baseline. Corresponding to each cases without AEB, 15 simulations with AEB were considered to the different FOVs and the AEB active time threshold. Without AEB, more collision could be found in scenario 3, when the pedestrian is occluded by the vehicle at the right side of the Eagle vehicle. The AEB system could still reduce the number of collisions significantly with the increase of the activation threshold. More collision could be avoided. The percentage of the impact speed once a collision occurred between the Eagle vehicle and the pedestrian was calculated for different AEB control conditions. The figure shows the higher impact speed could be observed under the no AEB conditions, leading to more severe pedestrian crash. In the case when the pedestrian is occluded by the vehicle on the left turn line, the impact speed getting reduced with the increase of the activation threshold. The collision locations, the distribution of collision point among different AEB cases in the same scenario are the same. As you more collision point are to the left side of the Eagle vehicle in the scenario 1 and 2. Since the pedestrian caused the intersection from left side of the Eagle vehicle with the increase of the activation time, the collision location tend to be at the left side. Similarly, more collision points are found on the right side in scenario 3 with the increase of the activation time. The collision location tend to be at the right side. Collision time. So in the same scenario, the Eagle vehicle without AEB has a collision with a pedestrian. The AEB could either avoid the collision or reduce the impact speed compared to the condition without AEB. A NOVA test has been conducted to compare the collision time under the two different effect conditions. Longer collision time could be observed for the collision speed reduction condition. It indicates that the occlusion could make the sensor unable to detect the risk condition and delay the activation time of the AEB braking system. Under the collision condition, the effectiveness of AEB could get reduced. So we also conduct logistic regression model. So here's the result. A Bellarmine variable is used to indicate if the collision is avoided or the impact speed of the collision get reduced. All factors except the FOV are all significant in this model. A collision could be more likely to get avoided if the pedestrian worked faster, since it takes less time for the pedestrian to cross the intersection and the collision time is less. The ego vehicle speed has the opposite effect on the effectiveness of AEB. A higher speed of the ego vehicle makes it difficult to reduce the speed to avoid the collisions. So expect the ego vehicle could brake earlier with a longer TTC threshold to activate the AEB and avoid the collision. The effectiveness of the AEB gets reduced if the pedestrian is occluded longer. Based on the effects of the TTC threshold to activate the AEB system and the occlusion, a longer TTC threshold is needed if a longer occlusion time is expected. Compared to scenario 1, effectiveness of the AEB system gets reduced in scenario 2 and 3, in which the pedestrian is closer to the stopped vehicle and easier to get occluded. Conclusions. So this study introduced an open source approach by using CARLA virtual simulator to evaluate the effectiveness of the AEB system under the occlusion condition. The evaluation was conducted by exploring the collision between the pedestrian crossing at the right line and the through vehicle, which is one of the most dangerous conditions at the intersection. 3 scenarios in which a pedestrian was occluded by stopping the vehicle on either the left turn or right turn line were generated for the evaluation. By considering the different motion status of the ego vehicle and pedestrian and the AEB control, a total of 10,368 cases were generated in the simulation platform. Different measurements, including the percentage of cases with collision impact speed of location and the collision location, were adopted for the evaluation, and the result suggests that AEB could still effectively avoid collision between the ego vehicle and the crossing pedestrian. However, the effectiveness of the AEB would get reduced by the collision. The results suggest that a longer TTC threshold to activate the AEB could be used to improve the effectiveness. Here's our future work plan. So we can add more different scenarios. For example, pedestrians are occluded by multiple moving vehicles. For example, pedestrians on the middle course doing the crossing with a PHP or other type of pedestrian lighting. So we also conduct the code simulation right now. As you can see on the right side, we get the Zheng data and calibrate with the real vehicle data and put into Sumo and then link to the CARLA. Last part is the cooperative perception. We are also doing the experiment right now. So we get the vehicle information from different angle of camera at the same intersection to send out warning to see if that can help improve the pedestrian safety.